Hello everyone. Welcome to today's quantum spacetime seminar. We are very happy to have Alex Belin from CERN and University of Geneva, who will be telling us about quantum chaos, OPE coefficients, and wormholes. Over to you, Alex.
Great. Thanks a lot. And thanks for the invitation. It's really nice to be giving this seminar. I've never come to India, actually, so hopefully one day things will be back to normal and we'll all be discussing physics in person, but for now, this will have to do. Great. So today I'll be telling you about some work that I'm really excited about that I've been doing over the past 2 years, say, with a bunch of great people, Jan de Boer, Diego Lisca, and Tarek Anous, who are all at the University of Amsterdam, and Julian Sonner and Pranjal Nayak, who are at the University of Geneva. And I wanted to start my talk with a quote from John Wheeler that I like a lot, which says that every law of physics pushed to the extreme will found to be statistical and approximate, not mathematically perfect and precise. And I don't know if this quote is true for all aspects of physics, but the message that I'll try to convey in this talk is that when we think about semi-classical gravity, it really seems to be applicable, and that the natural language to describe all of this is that of quantum chaos. Okay, so this talk is going to be about black hole microstates and their statistical properties. So if we consider a holographic conformal field theory, like say n equals to 4 super Young mills at strong coupling, well, one of the things that we would like to understand is the spectrum of energy eigenstates of that theory when you place it on a sphere. And so that's going to be a discrete spectrum, which is going to be extremely complicated. And I've mimicked it by this barcode here. So it's going to look something like this barcode here. So that's one of the things that we would like to know, the spectrum of the Hamiltonian. And another thing that we would like to know is, say, matrix elements of simple operators. So O here could be, say, a single trace operator. And we would like to know its matrix elements between two of these high energy states, black hole microstates. So I should say that, all of the states that I'm talking about here, they have energy of order m squared. These are very high energy states in the spectrum. And these matrix elements, again, are very, very complicated. So I drew a sort of a cartoon of a matrix here with which numbers that I guess you can't quite see, but they're essentially random numbers in some matrix. And again, that's very complicated. So all of these are the microscopics. They're very complicated. Not only do we not know what the individual eigenvalues are here, but even if I ask you how many energy eigenstates are there in a certain band, even that we don't know how to count from first principles in the strongly coupled quantum system. So that's the microscopic information, and it's extremely complicated. And the picture that I'd like to convey today is that the way we should think about semi-classical gravity is the theory not of the true microscopics, but rather of the statistical distribution of this microscopic data. So the statistical distribution of these energy eigenstates and of these matrix elements, these RMN. Okay, and part of this you've known for a long time. One could call it just black hole thermodynamics, or black hole thermodynamics applied to ADS CFT. And for example, the Bekenstein-Hawking formula for black hole entropy gives us a smooth function of energy, which is the entropy as a function of energy or as a function of the mass of the black hole. And what that does is count the number of states that exists within a certain energy band here. Okay, so it's not microscopic fine grained information, it's coarse grained. It tells us how many states there are in a certain band. And once you have the black hole background, you can also compute correlation functions on top of the black hole backgrounds. And this will be related to coarse grained information about the matrix elements here. It's not going to be individual matrix elements, but rather sum over many of these matrix elements. And there's also other types of things we can compute with gravity, for example, higher genus partition functions in 2D CFTs, and that gives us, again, more information, coarse grained information about these black hole microstates. Okay, and this is, I think it's important to stress that this is already quite remarkable, right? Because from the point of view of the field theory, we don't know how to count these states, but gravity does so in a particularly simple way. But like I said, this is something that we've known for a long time. It's black hole thermodynamics. But the picture that's coming to light, that came to light over the last couple of years, is that there's other geometries, wormhole geometries, that stretch between several different asymptotic ADS boundaries. And the picture that I'd like to convey is that they're giving us more refined statistical information about these microscopics, okay? In particular, higher moments of the statistical distribution of these true microscopics. Okay, so that will be sort of the main message in this talk today. And this has profound repercussions for the information paradox. Like Maldacena put forward, I guess, close to 20 years ago now, there's a form of the information paradox that applies to ADS CFT. And we can define a quantity, which is the spectral form factor, which is the analytically continued squared of the finite temperature partition function. And in fact, the thermal 2-point function, the autocorrelation function, also behaves very similarly. And how does it behave? Well, it starts at some value at early times, which is basically the square of the partition function. And then due to the phase interferences, because of this analytic continuation at time, it decays. And it decays and it decays. And if you use the black hole background to compute the spectral form factor or the thermal 2-point function, this decays forever and goes to 0. Okay? And Maldacena called that a form of information loss. And why is it a form of information loss? It's because in a true quantum theory with a discrete spectrum, this is inconsistent. You can check from very simple principles that, in fact, after sufficiently late times, once the signal is exponentially small in the entropy, you will start to have crazy erratic oscillations that oscillate around a non-zero value. Okay? So just any quantum system with a discrete spectrum has to look something like this if it's chaotic. And for a long time, we thought that semi-classical gravity would never be able to reproduce this. This part of the signal here is really due to having a discrete spectrum and is sensitive, for example, to eigenvalue repulsion in the Hamiltonian. And for a long time, we thought that we would never see this with gravity. But in the last few years, coming from the work of Sad, Schenker, and Stanford, we realized that actually, if instead of including just disconnected geometries when you compute the square of the partition function, if you include a geometry that stretches between two distinct ADS boundaries, you get this erratic part of the curve here has a pattern with a linear ramp. Its average is a linear ramp. And you can reproduce this linear ramp from a semi-classical geometry that looks something like this. Okay? And this is a form of information recovery. We see that the signal does not decay to 0, but rather starts to rise again. And we see it within semi-classical gravity. And like I was saying, this part of the signal here, this linear ramp, is due to eigenvalue repulsion in the Hamiltonian. And it's really remarkable that semi-classical gravity knows something about eigenvalue repulsion. Okay, so this was the new insight, that if you allow wormhole geometries of this type, you can recover information in some way, and see how you evade the black hole information loss paradox. But of course, there's a price to pay with this. Oh, there's a question?
Yeah. So
yes,
this gravity picture wouldn't reproduce the wiggles. They would just reproduce the ramp, right?
Correct. Very good. So if you want, the ramp is due to the 2-point function of the density of states. Okay, and it's sort of the coarse-grained version of this 2-point function, and there's further wiggles around it, which are due to higher moments. And these wiggles are there, and they're very big. And you can estimate their size by computing the square of the spectral form factor, which has 4 copies of the partition function. So you can learn about the size of these wiggles from semi-classical gravity. To reproduce the exact wiggles, that is, in other words, to reproduce the true microscopic answer, we don't know how to do that within gravity. Presumably, it has to do with branes and strings and UV ingredients that go beyond the low energy effective action. Does that answer the question?
Yeah, of course.
I can. Okay. Yes. Thanks. Yeah, please ask questions. It's a lot more fun for everyone, I think. So the talk is meant to be quite informal. Great. But like I was saying, so this is progress. We can see that with semi-classical gravity, we get, we don't get the exact microscopic curves that wiggles, but we get some sort of coarse-grained version of it. But there's a price to pay. And the price to pay is known as the factorization puzzle, which also is now older than a decade, which says the following, is that if you try to compute the square of a partition function in gravity, well, you'll have geometries that are just disconnected between the two boundaries. So a quantity like this involves two asymptotically ADS boundaries. So you'll have disconnected quantities, disconnected contributions. But if you include wormholes that stretch between the two boundaries, then the final answer that you compute will not look like a direct product of a function of beta 1 and a function of beta 2. And obviously, if you put just CFTs on two disconnected CFTs on two disconnected spaces, they don't interact. So you're supposed to get a direct product, which factorizes. So gravity seems to violate that. And because of this, people have argued that perhaps gravity is not dual to a definite quantum system, but rather to an average over Hamiltonians. And the picture that I want to give today is a different perspectives on this, which is based on quantum chaos. And it's not going to say that gravity is an average. It's just saying that, gravity captures the statistical distribution of the true microscopics, but not the true microscopics themselves. Okay, and as I explained in this talk, quantum chaos is really the natural language to be describing all of this. Very good. But what is quantum chaos? How do we think about it? Well, quantum chaos has several components to it. One of these components says that the Hamiltonian of a quantum many-body system should resemble that of a random matrix. In other words, the statistics of the energy levels in the true Hamiltonian should be the same as the statistics of the energy levels in a random matrix. Okay, that's one part of quantum chaos. And another part of quantum chaos, which is related to thermalization, is about matrix elements, and it's best formulated thanks to the eigenstate thermalization hypothesis ansatz. So what is the ETH ansatz? It says that if we consider matrix elements of simple operators, O, for example, if you're thinking about chaotic spin chains, O could be an operator that has support on just a few spins. Or if you're thinking about holography in n equals to 4 super Young mills, O could be like a single trace operator or a few trace operator. It says that these matrix elements, they have a universal structure. There's a diagonal piece proportional to some function f that I'll explain in a second. And then there's the off-diagonal pieces, which are proportional to another function g, and which are exponentially small in the microcanonical entropy. Okay, so let me explain every single term that's in here. Yes, there's a question. Yes.
So here, these energies are of order n squared, right?
Yes, these energies here are of order n squared, correct. Yeah. So this is really the high energy part of the spectrum. You could study what happens to matrix elements in low energy states, but those will have a very different structure, and there's no reason for them to have anything like this. In fact, the low energy part of the spectrum in n equals to 4 is integrable, so we'll have a very simple structure. Great. So let me explain everything that appears in the ETH ansatz. So f and g, I said, are smooth functions. F is just a function of the average energy, and it's related to the microcanonical expectation value of the operator O. The function g is a function of two variables, the mean energy and the energy distance. And it's related to it's basically the Fourier transform of the microcanonical two-point function of the operator O. Okay, and then RMN. What are RMN? RMN, people often refer to them as independent random numbers with zero mean and unit variance. Okay, so what is ETH telling you? How do you think about it? It's telling you that if you look at the matrix elements of this operator O, it's mostly diagonal. There's going to be a large diagonal piece, and the values on the diagonal are going to be given by the smooth function of the mean energy. which is the microcanonical one-point function. And then the off-diagonal pieces are very small. They're exponentially suppressed in the entropy. And that's the structure, that's the universal structure of this matrix. Okay? But there's a couple, yes, question?
In the context of n equals 4 Yang-Mills, will F0 be a smooth function of E or of E by n square? Similar question for G0.
So E bar will be of order n squared. It should be a smooth function of both, I think. I'm not sure exactly. Are you asking if you can resolve it?
It varies on scale 1 in the variable E by n square?
Yes, that's right. On scale, exactly. Its range is of 1 in units of E by n squared. That's right.
And similarly for G0?
Yes.
Both E and delta E are measured in units of n squared.
Yes, that's right.
Thank you.
Yeah, over a span of range 1. Yes, exactly. That's right. And so there's some things that I want to stress about ETH, which are not always emphasized enough, but I think are important. The first thing is that people say that these RMN are, people refer to them as random numbers. They're not really random. In any fixed theory, they're given. You know, if we had infinite power, say maybe one day with the bootstrap, we would solve n equals to 4 super Yang-Mills, and we would just plot this matrix, and there would be definite numbers. Okay, so they're not random. They're not truly random. I like to call them as pseudo-random, meaning that it's just that we cannot compute them. They're fixed in any theory. We cannot compute them, but they have a certain statistical distribution. Okay, so that's the sense in which they're random. They're pseudo-random. They're fixed numbers, but they have a given statistical distribution, and in this statistical distribution, they have zero mean and unit variance. Okay, but they're not truly random. They're fixed numbers in any given theory. Good. And the second thing that I like to emphasize is that, in fact, they're neither independent nor Gaussian. Okay, so the reason people say this is because often in the thermalization context, people are interested in computing the 2-point function, and to compute the 2-point function, all you need is the Gaussian part of the distribution. Okay, but if you really take them to be independent and Gaussian, you'll run into big inconsistencies. And in particular, as soon as you try to compute a higher point function, you'll see that to get the connected part of the higher point function, you need non-trivial correlations. So for example, for a 4-point function, you would need a non-trivial part of this particular cyclic connection, which is a non-trivial quartic moment, which ties different matrix elements. Okay? So it's not true that they're independent. It's not true that they're Gaussian. However, this is what is true. If you estimate the weight of the higher moments in the individual RMNs, you'll see that the individual weight is given by e to the minus k minus 1 over k times s for the kth moment. What this means is that the higher the moment is, the more and more suppressed they are in the entropy. Okay, and this was worked out in a very beautiful paper by Fournier and Kirchan. So the important part is not that they are truly Gaussian and independent, but rather that that's the leading approximation in an expansion in the entropy. And the higher moments have to be there, but they're smaller and smaller and smaller as you go to higher moments. Okay, but of course, you know, the individual weights are smaller, but when you compute a 4-point function, you sum over more intermediate states, so they can lead to competing effects. Okay, so this is a point that I think is important to stress. Good.
Sorry, Alex.
Yes.
Is there a understanding of the 3-point function where O is also a very heavy operator?
Oh, in the middle? This is going to be what most of my talk will be about. So yes, wait just maybe 2 minutes and we'll get there.
Okay.
Thanks. Very good. Okay, so this was all what I was discussing now was mostly about quantum mechanics and how we think about quantum chaos and quantum mechanics. But of course, we want to do ADS CFT, in particular in D greater than 1. So we want to understand how to apply this to CFTs. Okay, and quantum chaos then, so at the local level at least, the conformal field theory is completely specified by the list of scaling dimensions of operators and the 3-point couplings. Okay, so at least at the local level, we could say this completely defines our theory. So if we want to talk about quantum chaos in CFTs, we need to understand, okay, what is the set of properties that this list of dynamical data needs to satisfy? Okay, that will tell
Alex,
us how to.
I have a quick question about your previous slide.
Yes.
So the formula you gave there for the kth moment of Rmn, is that true for a particular class of, like, is that true in conformal field theories, or is that a particular?
Oh, so this should be true in all. Okay, so this should be true in principle in all quantum systems.
Okay.
But there's an assumption that goes into it, which is that the 4-point function is order 1. Okay. If the 4-point function is down by some power, that would affect that here. I think there is some, so you might already say, but in ADS CFT, the 4-point function is, or at least the connected part of the 4-point function is down by 1 over n squared. So you might think that you need to put some power of n down here, for example. And in fact, even that is not true, because if you take a Gaussian ansatz for ETH and you try to compute a 4-point function, say in a black hole background, there's going to be 3 Wick contractions that you can do. And with the Gaussian ansatz, you will get 2 out of the 3. You will not get the third one. So if you want to even get the third, generalized free field part, you need something like this without the 1 over n squared suppression here.
Okay, thank you.
Yeah, thanks. These are all great questions, so please keep them coming.
So just about that,
yeah.
Is it significant that the suppression goes to a constant as k goes to infinity?
Yeah, that's a great question. I'm not sure exactly. I think what it's just telling you is when you go to a very, very, very high point function, the cost of adding one more external leg becomes e to the minus s, just because there's e to the s states to sum over. So it's kind of natural. I'm not sure if it has a particular, so it doesn't go to a constant, in other words, right? It goes to e to the minus s. So the number in front of s becomes 1, and that's just because there's e to the s states, I think. I'm not sure it's more significant than that. Great. Yeah, I was saying that what we need to understand is what properties does this dynamical data need to satisfy for a CFT to be chaotic. So part of it we understand, because I said that the spectrum of the Hamiltonian should resemble the spectrum of a random matrix. And we know that the spectrum of the Hamiltonian on the sphere is given by the list of local operators. So the list of local operators should basically look like a random matrix. Okay, so that's the spectrum part of the story. And then for the OPE coefficients, part of the story is known, because if you look at the expectation value of an operator between 2 energy eigenstates, thanks to the state operator correspondence, you can rewrite that as a 3-point function. In other words, as an OPE coefficient. Okay, but as we said, the energy of these states here needs to be very large. In the thermodynamic limit, it needs to go to infinity. Whereas O is a simple operator, meaning that its scaling dimension is fixed. Okay, so in other words, this OPE coefficient has 2 heavy operators and 1 light operator. That's what ETH is predicting, that the structure of these types of OPE coefficients is universal. Okay, and another important thing that I won't discuss in this talk, but that one needs to keep in mind, is that ETH can only be a statement about primary operators. It's very easy to show that if you include descendants, off-diagonal descendants will completely violate the structure of ETH. That you can show very easily. So we should only be thinking about primary operators. And this becomes in particular subtle in 2D CFTs with zero-zero symmetry, but I won't really be discussing that too much today, but it's important to keep in mind. Okay, good. So we understood that at least part of this data needs to be constrained in some way by quantum chaos, but that doesn't tell us everything. And related to the question just 5 minutes ago, there's 2 other types of OPE coefficients which involve high energy states. The ones where all 3 operators are taken to be heavy, and also the ones where 2 of the operators are light, but 1 operator is heavy. Okay, and that's another part of the CFT data that has support on this high energy part of the spectrum, and we need to understand what to say about it for the theory to be chaotic. Okay, and it's easy to see that there are probes of chaos that one would like to define. So I'm going to just give you one example here. For example, in a 2D CFT, you can define a genus 2 partition function, which looks something like this. So it's a tripled sum over energy eigenstates with some type of Boltzmann weight here. But it's weighted by OPE coefficients squared. Okay, this is what a genus 2 partition function looks like in terms of the data of the theory. And then you can define a spectral form factor for the genus 2 partition function. Okay, And this should tell us about something about the chaotic nature of the theory. It's going to have both correlations of the spectrum and correlations of the OPE coefficient. And you can ask, what are the expectations from quantum chaos for an object like this? And the answer is we don't know yet, because there's no natural quantum mechanical counterpart for this. But it's something that we would need to understand. Okay, and so this led us to a conjecture, which we call the OPE randomness conjecture, which is a generalization of ETH to CFTs. It includes ETH and has more info in it, which says that all OPE coefficients involving heavy operators are random in a chaotic CFT. Okay, so in particular, the light heavy operators are also random. There's no diagonal part here. There's just a random variable with, again, a smooth function of the energy. And for the heavy OPE coefficients, you get, again, no diagonal piece. There's just a pure random part with a smooth function of the mean energy and the various energy differences. Okay, and now these things should be understood as, again, pseudo-random variables with zero mean and unit variance.
Sorry, the first OPE coefficient, these O's are the same operators, or O and O?
It doesn't matter. Yeah, it should really be, I should have really called them like O prime, and this would have been a function of O prime. They don't need to be the same.
Okay.
The simplest one is the case where they're the same. Yeah, thanks. Okay, so that's a conjecture. It would be very nice to prove it. It's going to be obviously very difficult to prove. So the ETH ansatz, even in quantum mechanics, has not been proven. What you can do is you can take a chaotic spin chain and do direct diagonalization and check numerically if it seems to be true or not. And there's a lot of people that have done that over the years, and it seems to work extremely well. For chaotic CFTs, it's much harder because we don't know how to solve chaotic CFTs. What I'll be doing later in this talk is trying to give some evidence for this, but of course it's going to be very hard to prove from first principles. Okay, but that was all about sort of a conjecture about the statistical data of conformal field theories, but what is the implications for gravity? And what we proposed is that what is semi-classical gravity? It's the theory of these smooth functions. Okay, it's the theory that's capable, it's a machinery, it's a tool that can compute these smooth functions, and in principle higher moments as well. But it can do no more than that. It can never actually resolve the microscopic numbers, which would be resolving the individual values of these random variables here. Okay, and because it cannot do that, it explains the lack of factorization. To get all these wiggles that we were talking about earlier, you need the true microscopics. Gravity cannot do that. But what it can do is compute, in principle, the all-point moments of these signals. Okay, so that's the proposal.
Alex, sorry.
Yes.
In the off-diagonal part of the EOE, you had a suppression factor with an entropy.
Yes.
In these two new conjectures, you don't have such a suppression factor.
So that's the question, and that's one of the things that I want to give evidence for today. So again, so what does this mean here? When I say that they're pseudo-random variables with zero mean and unit variance, just like for ETH, we know that this cannot be strictly true. The idea is that this would be true in an approximation. And what would need to be true for this statement to hold is that the higher moments are further suppressed in the entropy, just like for ETH. And at this stage, it's a question mark, and that's one of the things that I want to give evidence for today. Okay. So
another question.
Yes, please.
Saying that the gravity dual calculates all point moments of the wiggles.
Yeah.
So if all point moments of the wiggles can be calculated, then essentially the effect of the wiggles can be calculated completely, right?
I'm not sure about that. I think this is like known somehow as the moment problem. I think it's not true that you can always reconstruct the signal exactly.
From the moments, you can't.
From the moments, it depends on various things. And in particular, you might think that there's limitations to what I'm saying when, for example, you start inserting n boundaries. So maybe you cannot really compute the arbitrary point moment. Maybe what you can do is you can compute any fixed point moment in the limit where n goes to infinity. You see, so there's a sort of order of limits issue, if you want. So I don't expect us to be able to compute really the details of the signals this way.
Okay.
But I think there's a known math problem about this, about reconstructing something from all the moments, and well, there's some cases where it works if you have like a finite dimensional matrix or something, but there's other cases where it's much more subtle. Good.
Sorry, Alex, just going back to the no suppression here. Can you give some intuition for why you expect two heavy and one light to behave sort of so differently from, let's say, three heavies?
Sorry, what do you mean by so differently?
Meaning the two heavy and one light, apart from the diagonal term, was very small, right? Had an
very good. Yeah, sorry, I didn't say. Okay, yes, very good. So there's a question of how big this thing is, right? So far, I've said nothing about this. This is just some smooth function. And in fact, this itself is exponentially suppressed. So there's a sort of problem of notation. So the way I like to write the ETH ansatz, I like to put the function g, which is somehow, something like this. So people often factor out the exponential piece. You could have just put a function there without saying how big it is. And here it's going to be the same thing. There's an e to the minus s hiding inside this. So it's itself very small.
I see. And in the first function, is that also small?
Same thing. This is also e to the minus s over 4, for example, in 2D CFTs, I think.
Okay.
So these things are individually very small.
Thank you.
Yeah.
Alex, one quick question. In random matrix theory, when we say the Hamiltonian is a random matrix, we mean that the spectrum is kind of random, but we also mean that the eigenstates look random, right, in the unitary ensemble.
Absolutely.
So is that should I think of this OPE conjecture as capturing that part, like the eigenstate part of the Hamiltonian? Or
yes, I will discuss. Maybe you can hold off your question for just like 10 more minutes. I will discuss something related to this, and just hold off for your question, but the short answer is yes. Part of these random correlations you can explain by the correlations coming from the change of basis between that of an operator, but you have to do it in a bit of a funky way compared to ETH. Hopefully I'll get to that.
Okay, thanks.
Thanks for all your great questions. This is making the talk very interactive and fun. At least for me, I hope it's the same on your side. Great. So the plan is pretty simple for what follows. I want to give some evidence for this OPE randomness hypothesis, and then discuss some implications for gravity and wormholes. Okay. So the question is, how can we check ORH, right? And I was saying for ETH, at least on spin chains or for the SYK model or something like that, you can just do it numerically, right? You work with a finite dimensional matrix, you diagonalize, and you go from there. In CFTs, this is too hard. And what ideally one would like to have is one day the numerical bootstrap to be powerful enough to be able to capture, the OPE coefficients of very high energy operators up to an exponentially small accuracy. Okay, but this is way beyond the current capabilities of the bootstrap. Okay, for now, they can do a few operators above the vacuum, but not parametric separations and not to exponential accuracy. So we can't directly probe this or check if it's true, but we can look for consistency checks, okay? And in conformal field theories, the dynamical data of the theory, the OPE coefficients and the spectrum, they're constrained by crossing symmetry and modular invariance in 2 dimensions, okay? And there's a way to encapsulate this dynamical data in a very simple way, and this goes in the names of asymptotic formulas. So the most famous of these is Cardy's formula, but there's another one relevant for OPE coefficients that I'll discuss now that was worked out by Papadoulou and all, essentially 10 years ago. If you consider a 4-point function of 4 identical operators, say for simplicity, and you look at the OPE limit where O goes to O, in that limit, you're dominated by the identity exchange. And then you can ask, how is that reproduced in the cross channel? And in the cross channel, yes.
This identity is the full vacuum Virasoro, right? Not a global block.
Oh yeah, in principle. So in principle, there should be blocks on both sides of this equations here. In the limit where you take the OPE limit here, you don't even really need the block because you're going to a limit where it's actually just one operator that you're keeping, not even the block. I'm really imagining going to a limit where you just keep the lightest possible operator that couples to O and O.
No, but when the two O's are identical, that would be the identity.
Yes.
So you are keeping only the identity piece?
Yeah, only the identity piece. You know, you're right that there's a whole block, but so it's, for example, in 2D CFTs, there would be a whole 0-0 block, but the stress tensor will be itself suppressed compared to the identity, for example, because, you know, we're really taking the OPE limit where the operators are on top of one another, and that will suppress all the leading terms in the block.
I see. And
but the block will be important on the right-hand side here.
But all these blocks, do I have to think of them as Virasoro blocks, or I can think of them as global conform blocks?
For now, here I'm in general dimensions, so here we should think about global conformal blocks, and then the story gets refined in.
Okay, fine. So this is just the disconnected 2-point function on the left-hand side. Then.
Yes, that's right. Exactly.
Yeah,
I see. But this is some standard generalized free field kind of stuff, right?
Well, there's a very long story here that I won't have time to explain. If you go to the light cone limit, then there's an approximate generalized free field sector that emerges at large spin in all CFTs. But here I'm just doing the simplest thing, which is just the Euclidean bootstrap. So I'm on the Euclidean plane and I'm taking the two operators to one another, two pairs of operators towards one another.
Yeah. Sorry. Yes.
Yeah, no worries.
I have a related question.
Yes.
So finally, when you are going to compute the left-hand side, you are just going to say that it's equal to 1 by the displacement between the O's on each side, right? The square of so that's essentially you're assuming that it's a free theory.
No, not necessarily. It's just that I'm keeping only the identity. So, you know, in all CFTs, you're going to have a term like this, and then whether the theory is free or not depends on what the ... is here. But in all CFTs, you're going to have the 1.
Yeah, so you'll be ignoring the ... right?
Yes. And what I'll say right here, yes, I'm ignoring the ... correct.
So in that limit, it would be a free theory. Essentially, assuming that it's a free theory.
Well, I would say it differently. In that limit, you're not able to tell whether it's a free theory or not. I think that's how I would say it. This applies to all CFTs. Maybe I'll say a little bit more about that in a second, in how to think about these asymptotic formulas. Yeah. So related to the question. So what you can do is you can ask, how is the identity reproduced in the cross channel? And you can convince yourself very easily that it cannot be done by a single heavy operator in the cross channel. What really has to come is from the collective behavior of many heavy operators in the cross channel. And that enables you to derive an asymptotic formula for the light, heavy OPE coefficient squared. Okay. And so this was done in this paper by Papadoulou et al. From 10 years ago. And of course, you know a version of this in 2D CFTs from way before by Cardi, right? If you look at the torus partition function of a 2D CFT, you look in one channel, you keep just the identity, you go to a very low temperature limit. In the cross channel, it's a very high temperature limit. And for you to match what you get, you need to have a certain entropy. And that's how you derive Cardi's formula. Okay, so this whole business is known as asymptotic formulas, and there's really been a lot of them in various contexts, various dimensions, various number of operators, and so on and so forth.
I have a question.
Yes.
Like, I suppose the understanding is that the O's on the left-hand side are very near to each other. So that is why you can take that limit. It's not, it's not, if it was a free theory, then it wouldn't make sense in any case.
Yeah. No. So this is meant to be in the OPE limit. So I didn't write it, but yes.
Exactly. Yeah.
Yeah, so these are going to one another, and these are going to one another in position space.
Yeah.
Very good. So there's many asymptotic formulas that you can derive this way. There's one formula that will be relevant for this talk, which is an asymptotic formula. This time not for light, heavy OPE coefficients, but for heavy OPE coefficients, which is derived from modular invariance at genus 2, which was done in these papers here. And it has the following form. I've sort of expanded it at large C here for simplicity, but there's a known formula at finite C. And maybe to answer Shiraz's question from earlier, you see here that there's an exponentially damped piece. And here you sort of recognize Cardi's formula. This is like e to the minus 3s over 2. So this and this function here, you should think about it as the function or the square of this function f that was appearing in the ORH ansatz. These types of formulas that you derive here, they're constraining the variance of these OPE coefficients. Okay. And maybe related to the question that was just asked, it's important to stress that these formulas are derived, they apply to all CFTs. Okay. In particular, they apply to free theories. So they don't prove the OPE randomness hypothesis, right? They don't, because the OPE randomness hypothesis is a statement about the size of the individual terms. And in a free theory, what will happen is that many of these OPE coefficients will be zero because of selection rules, and some will be gigantic, such that the average looks the same in a chaotic theory where we expect them to be all roughly the same size in random. Okay, but it's sort of a consistency check of what crossing applies on the various moments of OPE coefficients.
Sorry, could I ask what's probably very stupid?
Yeah.
Suppose we were, as Abhijit was talking about, in a free field theory in ADS, meaning the bulk was free field. Then would this would the equation that you have on the third line, the one you've written in a diagram, would that equation not be satisfied just by including single and double trace operators?
It would, yes.
But in that case, do you have does your COOH have all the properties you wanted?
No, it doesn't. So this is exactly what I'm saying. I'm saying just deriving this formula does not prove ORH, because you're going to have other theories that have a very non-chaotic spectrum and a very non-chaotic OPE coefficient that still satisfy it. But what it does, it just tell you in all CFTs what the variance is, and then what'll happen is that in chaotic theories, the higher moments will behave maybe very differently than in a chaotic one. For example, if we were able to compute something like COOH squared, maybe that will start looking different, for example, in different theories. So it's really, indeed, what I'm saying is that these asymptotic formulas, they are compatible with free theories. Okay, so they don't prove the OPE randomness hypothesis. They just tell you that just conformal invariance or crossing symmetry constrain the dynamical data in some way. And you can check if the way in which they constrain it is at least compatible with something like the OPE randomness hypothesis.
Okay, thank you.
Sorry.
Yeah.
I have a question. Like, when you are saying that it would be valid for free theories, on the right-hand side, how would that work? Because on the right-hand side, you wouldn't have any exchanges for free theories, right? Oh
no, you would have O squared. So you would have O squared and all the derivatives. So you would have the operators O squared and L.
No, on the right-hand side, if it was a free theory, then there are no trilinear couplings, for instance.
No, but there's double trace. There's so let me try to draw it here. This again. Okay. Well, let me do it up here. So if you're in a free theory 5-5. Okay, and here I said there's an operator H. What is H allowed to be in a free theory? H is going to be phi d mu L phi, right? It's a two-particle state, right?
How is it a free theory anymore?
It's still free.
In the Lagrangian, you would have to have such a term.
No, it's still free. It's just in a free theory, you can ask, how are so in a free theory, if you compute a 4-point function, you have 3 Wick contractions. And you can ask, how are the other 2 Wick contractions reproduced in one OPE channel? And it comes from summing over operators of this type. The theory is still free because these couplings are completely fixed. So, it's just the 3-point function in a free theory between 2 1-particle states and a 2-particle state is not 0. It's a fixed number given by combinatorics, but it's not 0.
Show me that it's just a Taylor expansion of phi of x, phi of y around, let's say.
Yeah, that's another way to say it. Yeah.
So if you have this phi del mu, etc. phi term, then that's still a quadratic term. It wouldn't give rise to a trilinear vertex.
No, exactly. You're right. So I'm not saying that phi is non-zero. That's not true. Phi remains zero, right?
Yeah.
I'm not saying that, but it's not because the trilinear couplings of phi are zero that means that all OPE coefficients are zero. That's not true because there's two particle states, and the OPE coefficient between two one particle and one two particle state. So in a free CFT, phi and phi squared, that's non-zero, even in a free theory.
Okay. Yeah.
Good. See what I'm saying?
Yeah.
Good.
Alex,
yes.
Sorry. So this last formula here, this is sum over IJK heavy operators, right?
Yeah, all three heavy. Yeah.
And the delta is what? Is delta average dimension?
So all of these, yeah, maybe I should have written that. So all of these, let's say we sum over them in some band around some dimension delta, and that's the delta that enters here.
I see. And width of the band is some small number in the delta unit.
Yeah, you mean the size of the band? Yeah. It's like in Cardy's formula. In Cardy's formula, we write rho of delta.
Okay, that's what I say. Okay, got it.
Yeah.
So the generalized free field OP coefficients do satisfy this equation, right? In particular.
So this is important now. The generalized free field OP coefficients, they satisfy this one because that only relies on crossing. They do not satisfy this one because you have to remember that generalized free fields are not modular invariant.
Oh, sorry.
And this comes from modular invariance.
So I don't want to talk about this equation. I just wanted to talk about where the generalized free field are a solution.
Yeah,
here.
Here.
What is that equation? I guess you didn't write it.
I didn't write it. It's like
so. This is equal to some delta thing, right?
Yeah, it's like 1 over delta. It's delta heavy to the 2 delta light minus 1 or something like that.
Okay. So this is satisfied by the
generalized free fields, absolutely.
But the statement is that because it follows more generally, it is true. You would like to say in some chaotic theories also.
Yeah. So I think here's the picture in a generalized free fields. How is this going to work? So in a generalized free field, there's tons of operators at high dimensions, right? There's many powers of phi, for example. But we know that the only operators, so I guess I didn't write it here, but there's also a row of delta H. Okay.
Yeah.
So in a free theory, what happens is that the formula is still the same, but when the operator H is a two particle state, the OPE coefficient is gigantic, and when it's a 3 or more particle state, it's exactly 0. And the entropy is counting mostly many particle states at that stage, right? So on average, so what this means is most OPE coefficients on are 0, and then there's very special states where the OPE coefficients are huge. That's how it works in a free theory. In a chaotic theory, what we think happens is that all the OPE coefficients are roughly the same size, and they all contribute collectively.
Yeah, I see.
That's the picture. So the asymptotic formulas are true in all theories, but how they're realized is going to be very different in a chaotic theory.
So I just wanted to ask, basically, given that the generalized free field is a solution, could it be that higher moments also, if you want to conjecture the higher moment, could you just conjecture it to be the higher moment of the generalized free field coefficients? Because in any case, that is a solution.
Very good. So it depends if you can derive the higher moment from a crossing equation. There's no crossing equation that I know that will isolate something like this. This is just new, right? Because this is like you take the intermediate thing in a 4-point function and you just square it, right? If you compute,
let's say you consider some higher point functions and such.
Yeah, well, exactly. That's where I'm going to get to.
Right?
Yeah, okay. That's where I'm going to get to. And indeed, it will whatever you write down, if it comes from a higher point crossing equation, has to be at least compatible with GFF. Always.
Okay, great. Right. Thanks. Yeah, that's what I wanted to know.
Sorry, one probably stupid question again. The COOH is the thing that you said should be of order e to the power minus s by 4 in your.
Yeah, good. So this is where, okay, yeah. So this formula that I wrote here is a formula that applies to for global primaries in all dimensions. If you write down the formula for Virasoro primaries in 2D CFTs, then it's a different formula. So in that case, so here, right here, you have a 1 over rho. So the individual OPE coefficients go like e to the minus s over 2. But if you write down the equivalent formula for 0 primaries in 2D, then you get e to the minus s over 4. It's because of the blocks, basically.
Okay. Yeah, so s over 2, I understand. It's just to cancel. So that's s over e to the power minus s over 2 square cancels the density of states.
Exactly. Very good. Okay. So I'm running wildly behind, but that's fine. I don't need to cover everything. So we can ask,
so Alex, just to let you know, we are flexible on kind of flexible on time, given that there are so many questions. So usually the talks do go over time.
Okay.
So
good.
if
Then
you have
I'm also not constrained. So we'll see. I don't want to start boring everybody to death. So I'll try to finish not too much behind, and then we can always discuss after the talk. Okay. So what I wanted to do is try to show you that the higher moments are suppressed, at least in certain cases. And from now on, just for simplicity, I'll focus on d equals to 2. But some of the things that I say can be extended to higher dimensions, not all of them, but some of them, okay? And the idea is that we're going to try to exploit modular invariance on higher genus surfaces or crossing symmetry of higher point correlation functions to constrain the higher moments, okay? And there's a very nice technology that was developed in this paper by Collier et al. Called involving the Virasoro crossing kernel. And the Virasoro crossing kernel method is the following. So, if we have a 4-point function, we can expand it in the S channel like this, or in the T channel like this. And each channel has its own Virasoro conformal blocks. Okay. And one difficulty in doing this program in 2D CFTs is that we don't know Virasoro conformal blocks in closed form. We just don't. Okay. But what you can do is you can write a formal formula, which is a change of basis going from the S channel to the T channel, which looks like this. Okay. So it's a formal formula, and the change of basis operator, if you want, is called the crossing kernel, okay, or the Virasoro 6J symbol. Okay, and the beauty of this story is that even though the conformal blocks are not known in closed form, the crossing kernel is known in closed form. Okay, and it was written down by Ponsot and Teschner. Okay, it's a relatively complicated function. It involves ratios of digamma functions, but okay, it's nothing too nasty. I mean, mathematics knows how to deal with it just fine. Okay, so we know it exactly. So then, and I should have said that this is for the crossing kernel, but for the modular kernel that implements modular transformations, it's also known in closed form. Okay. And so from this, there's a strategy that you can use to use the crossing kernel to extract, moments of OPE coefficients. Okay, so let me just show you first how it works for the genus 2 surface. So you have a genus 2 surface. I'm going to write it in this sort of trivalent diagram way. Okay, and each number here that I'm writing is one state that propagates in a loop. Okay, and so we would like to estimate the OPE coefficients, C1, 2 squared, where 1, 2, and 3 are heavy. Okay, so how do we do that? First, we apply the crossing kernel to this genus 2 surface, and we send 2 to 2 prime. We arrive at this diagram here. And then we apply a modular transformation to each of the 1 and 3 loops, which sends them to 1 prime and 3 prime. Okay. And then what we do is we send all of these primed operators now they're in the cross channel, if you want. So we send them to be the identity. And that will tell us about what the high energy dynamics is in the original channel that we have. Okay. And so what this schematic diagram tells you is that the OPE coefficient squared is just given by F times S squared. And like I told you, F and S squared are known in closed form. Okay, and this is what was done in this paper by Collier et al. But now the really nice thing is that on any genus surface, these crossing kernels, F and S, they act locally. Okay, so what you can do is you can work at arbitrary genus and write down a recursion formula that, by applying a series of moves like this, takes you from a genus G surface to a genus G minus 1 surface. And I'm just going to go over that very quickly here. This is a genus G partition function expanded in what we call the skyline channel, because it kind of looks like New York. Okay, and so you can do a series of moves now. First, you do a crossing move for the operator 1, and then you get a slightly different surface like this. Then you use a crossing move again, this time for the operator 3. And now you produce a genus G surface, but with a slightly different topology. And then you do an S transformation on the operator 4 to make it light. And now we're going to send 4 prime. I guess I wrote it here. We're going to send 4 prime equals the identity, 3 prime equals the identity, and 1 prime is then forced to be 6. Okay, by the fusion rules. Okay, and so you see what happens is now you have a skyline, but without the tallest building. Okay, so this is, if you want, this is like a recursion formula that says like genus G equals FFS times genus G minus 1, G minus 1. Okay, so it's a recursion formula, and then you can just solve very easily that recursion formula. You knew what it was at genus 2, and you can write down an all genus expression for the OPE coefficients. So this is the moments of NC OPE coefficients expanded in the skylight channel when all operators are heavy, and it's given by, now I've written down the exact finite C version of the formula. It's given by this. Okay, so this is a new asymptotic formula involving arbitrarily many OPE coefficients. And you can play the same games on the plane with higher point functions. So here's something coming from higher point functions on the plane, and it involves a combination of light, light, heavy, and heavy, heavy, heavy OPE coefficients. And again, you can derive an exact formula.
I have a question.
Yes.
Where is the genus counting parameter coming in here?
Oh, it's in NC. It's in NC. I think a genus, let's see, can I get it right? A genus G surface involves, or the number of OPE coefficients is 3G minus 3 divided by 2, I think, or something like that. So there's a formula that relates NC to the genus. The bigger NC is, the higher the genus is. And here, what's counting the number of light operators is M. There's basically, M plus 2 over 2 light operators in this formula.
So the second formula is coming from the plane, you said. What does that mean?
Crossing invariance on the plane of M plus 2 over 2 point function.
Okay. And this is also in 2 dimensions with Virasoro stuff, right?
Yeah, both of these are in D equals to 2.
Yeah, okay.
In higher dimensions, we were able to find a formula from the 6-point function on the plane, but only for all operators of the theories, not for primaries, because we didn't know the 6-point blocks.
So just one question then. Given that, again, I mean, can one run a similar kind of argument to say that if you take, for example, a rational conform field theory, Ising model? Yeah. Well, no, sorry. This is, you want heavy operators. Okay. Yeah.
Yeah, and here it is important that we have C greater than 1 here.
Yes.
This Virasoro crossing kernel works for C greater than 1, so you won't be able to do it for the Virasoro minimum models.
No, but for example, some compact bosons, a bunch of compact bosons, something like that. Well, no, not. Yeah.
So you could do it for a bunch of compact bosons, and the formula would be true, and it would be sort of the same story as we were saying before. Is that
right?
The asymptotic formula is true, but the way it's realized is going to be very different than in a chaotic theory.
Right, but let's say if one's aim is to get the formulas, then one can take something that is realized, and then take its asymptotic limit, and one should expect in general this to be true, right?
Yeah.
Okay, thanks.
Yeah, absolutely. Yeah.
So how are the moves going to determine the dependence on the genus? Because the ultimate formula depends on how you take the moves, right? And they would vary from genus to genus. So
what I said here is that in the skyline channel, there's one move that you always do, and once you've done this move, you do the same one to remove this, and at the end of the day, you're going to be left with something that looks like this.
Yeah, precisely, and that is going to differ from genus to genus, right?
No. So I think what you're asking is that there's a skyline channel that exists at all genus, and that's what we're extracting. But at any fixed genus, there's of course many different topologies of OPE coefficients. And we haven't figured out a way to extract all of them. So this is one particular contraction of OPE coefficients. But this contraction exists at all genus. You see what I'm saying?
Then how does the dependence on the genus come about?
It's here. It's in the number of OPE coefficients. So, you know, I said that we had, so, you know, what I was saying is that we have something like, you know, G equals FFS times G minus 1, right? So that's a recursion formula. So it just tells you that you're going to get basically something like this. Okay, this is a bit schematic, but, you know, the higher, you'll just get the F times S raised to a certain power.
True, but that is just going to depend on how many operators you have, not the number of genera, right?
But they're related. The number of OPE coefficients and the number and the genus are related.
Okay, so how does that?
I can't give you the exact formula, and I think it's like 3G minus 3 divided by 2, I think, is the number of OPE coefficients or something like that. Or maybe, yeah. Well, there's the number, that's the number, 3G minus G is the number of heavy operators that propagate, and then you need to split them up between the OPE coefficients.
So you're saying that the number of operators that propagate depend on the number of genera?
Yes.
Why is that?
Oh, just because in every loop, so, you know, here's a cartoon of a genus surface. In every one of these loops, there's a new operator that propagates.
But that's the final expression. I mean, in the original expression, it might not be like that. It might be some arbitrary surface, right?
Yeah, but still, in every circle, there's a state that propagates. That's just the pair of pans decomposition of a genus G surface in a 2D CFT. It's like the Seiberg and Moore prescription. So there's the higher the genus, there's always going to be more intermediate states that propagate.
Okay.
Maybe I can go on.
Yeah, sure.
Because, yeah. Okay, so the question that we really wanted to understand with all of this business is how big the non-Gaussianities are.
Sorry,
right?
Alex, just kind of a one. I mean, I guess it's a bit of a philosophical question, but here you are interested in drawing up a criteria for chaotic CFTs, right?
No, not quite. I mean, that's what I would really like to do. But as we just said, you know, when writing asymptotic formulas, because they're true in free theories, this is not going to be the right criteria to distinguish. What I wanted to do here is check whether, you know, at least the constraints coming from modular invariance or crossing symmetry, are they even compatible with something like the ORH in the first place? You see what I'm saying? It's not, we're not developing a criteria for chaotic CFTs. We're just checking if, you know, if our conjecture is at least compatible with the basic axioms that the theory needs to satisfy. And if it is to work, it means that the higher moments need to be suppressed.
Okay, thank you.
Yeah.
But ORH itself, you don't expect.
No, we won't be able to prove using anything like this. In fact, I think
you don't expect that to be true in free theories, right?
No, exactly. We know it's not, in fact. Yeah. Very good. So you can check how big the moments are, and if you take this formula and you divide by the number of OPE coefficients and so on and so forth, you get that the kth moment is suppressed by e to the minus 5k minus 1 over 4k times s. And indeed, the more you increase k, the more suppressed the moments are. Okay, you should remember that the formula for ETH was k minus 1 over k, and so you have different integers here. Okay, they're not exactly, they're different numbers. They're not exactly the same as what you had for ORH, and that really comes because of the black box of the crossing kernel, but we do see that they are further and further suppressed as you increase the moment, okay? So this says that at least, you know, something like the ORH hypothesis is at least not inconsistent with the constraints coming from modular invariance and crossing symmetry. And I didn't write down the expression, but the same is true for higher points on the plane. Okay, and now I'm gonna come back to what Ankar was asking a while ago. I guess I said 10 minutes, maybe it was more like 20. But you can ask, you know, whether something like ORH, you can derive it from random matrix theory. And there's the way where this works in ETH. So if you take an operator, okay, let's expand it in its eigenbasis. So now I'm back in quantum mechanics for a second. And then you can look at the inner product between an eigenbasis of O and an eigenbasis of the Hamiltonian. And if we're going to average over Hamiltonians, this is basically a Haar random unitary, this change of basis. Okay, so then you just plug this expression in here, and you get the following expression, and then you can do the Haar average over the actual Haar average over the unitaries, and you'll see that in that case, so assuming random matrix theory, you'll see that the 1-point function of O has to be diagonal times a coefficient, which is just the microcanonical 1-point function of O. So if you want, this is a way to, it's not quite deriving the ETH ansatz, but it's a big part of the intuition that went behind the formulation of the ETH ansatz in the first place. And it comes from random matrix theory. And the question, and I guess this is what Ankar was asking, was, you know, how does this work for ORH? Can we do anything from random matrix theory? And so what you can check is that if you define a linear operator on a tripled Hilbert space, okay, so you have to play some kind of trick. So what we can do is we can define an operator on the tripled Hilbert space whose matrix elements are the OPE coefficients. Okay, so we triple the Hilbert space and then we define some operator on it whose matrix elements are the OPE coefficients. And then we can imagine that we try to fix this operator, okay, and do Haar averages over the change of basis between O and the Hamiltonian. Okay, and then if we do that, what we showed is that you can derive ORH type correlations. In particular, you know, CIJK CLMN will just be given by a bunch of Wick contractions. So the indices need to pair up times the coefficient, which is just the trace of O, which is just the asymptotic formula for C squared. And then you can study the variance and see how small the variance is. And you'll get that the coefficient of the non-trivial variance is given by the trace of O in the sunset diagram. So this particular combination of OPE coefficients, but again, it's suppressed in the entropy. And it's suppressed in a way that is not exactly equivalent to this, because somehow part of these numbers here come from the magic of Virasoro blocks. And in doing this RMT trick, you know, we're blind to all of this. We're just doing random matrix theory. So we're dealing with everything as primaries in some sense. But we do get at least, you know, qualitatively the structure of higher moments being suppressed. But this is a little bit of a cartoon because what we're doing here is we're sort of assuming that the OPE, so, you know, if there was an RMT formulation of conformal field theories, we would expect that as we integrate over something, both the OPE coefficients and the Hamiltonian get averaged over. And here we're doing some kind of cartoon where we're fixing the OPE coefficients and averaging over the Hamiltonian. Okay, but at least we can derive things that look schematically like the structure of ORH from this. So I don't know if this answered your question from before, Ankar, but it is certainly something that you can do, and it gives you all the right correlations that you expect.
Yeah. Thank you, Alex.
Great. So I'm already pretty much over time. What I could do is just stop here and maybe pause for questions, or I would need like 10 more minutes to discuss the gravity part.
Alex, you can go on.
Yeah, you're sure?
Yeah.
Okay, I'll try to be not too long. So now I want to discuss the implications for gravity. Okay, and I'll do that for the sort of simplest wormhole.
Alex,
yes.
One minute, I'm trying to understand some counting. So
yes.
Is it right that the genus 2 surface can be thought of as two 3-point functions glued together?
Yes.
So I expect the genus 2 surface to be sort of order 1. And I have to sum these 3-point functions over 3 operators. So should I have expected that C squared times e to the power 3s scale like 1? So C scales like e to the power minus 3s by 2?
Oh, yes. Yes, it's a bit more subtle than that because the genus G partition function doesn't really scale at like 1, right? It's itself, where can I write this? Maybe here. Oops. So, you know, Z, so remember that even for G equals to 1, it's not true that the torus partition function scales like 1, right? It scales like e to the minus c over 12 4 pi squared over beta at small beta, right? And there's a similar expression for the genus 2 partition function.
Right. Sorry, but I was thinking of just not taking beta particularly small, but still you have contributions from very heavy operators all the way.
Oh, okay, you want to say, let's take beta of order 1, say,
yes.
And then you get an order 1. Okay, very good, I see. Then you're saying we get an order 1 number, and there's 3 states, and they need to be, so there's 3 density of states, everything is order 1, and that gives you the e to the minus 3s over 2.
So is that the right scaling? C is e to the power minus 3s over 2?
Yes, it is. So the formula forCijk squared, it goes like e to the minus 3s over 2. Ah, good. Yeah. So here I see your confusion, but then you're going to say, okay, but now let me add 3 powers of the density of states, and I don't get 1. I get something that looks bigger, right?
No, if it's e to the power minus 3s over 2, that's perfect, because 3 powers of the density of states is e to the power 3s, and then 2 powers of e to the power minus 3s over 2 is 1.
Yeah, but here I already wrote for the square of OPE coefficients, not for just the individual one.
Yes, then I'm confused. Yes.
So then it looks wrong, but what's confusing you is the conformal blocks. The conformal blocks are not doing nothing in this story. Okay. They're responsible for part of the factors of the entropy.
Okay, fine. So if I included, if I did SL2R kind of counting, then this would be correct.
Yes, absolutely. Yeah.
I see. Fine. And one more along these lines. Suppose I computed a 2-point function on the torus.
Yeah.
And my 2-point function is of a light operator.
Yeah.
Then that looks to me like it would get contribution from 2 heavies, sort of 2 Cijks, which are 1 light and 2 heavy, sort of squares.
Yes. Correct. Yes.
And this would then explain the e to the power minus s by 2.
Yes, it does. And it's just a miracle, or I don't know what you want to call it, but the conformal blocks in that case, the blocks on the torus, don't give you extra factors. So in that case, you know, the what you would expect just from state counting actually is also the size of the primary OPE coefficients.
Okay. Yeah. So now I understand your intuition. You could basically just saturate these things with density of states, and what you get there is a reasonable conjecture. Right?
Exactly. And then I think, so if you want, the conjecture is then just to say that, so this is just counting of states or counting of OPE coefficients. And then the ORH conjecture is just to say that, you know, individual terms are not going to be bigger or smaller than any other. They're all just sort of going to be averaged out in some way. And that's what it is.
Thank you.
Yeah, great. Okay. So now let me shift gears and go to gravity. And the wormhole that I want to study is what I like to think of as the simplest possible wormhole. It's a wormhole in 3D gravity. That stretches between 2 genus 2 surfaces at both boundaries. And it's so simple that I can write down the metric for you here. Okay. So rho is like a holographic coordinate that goes from -∞ to +∞. And this is the constant curvature metric, which is negative, that has negative curvature on genus 2 surface. Okay. And so this is a very nice wormhole. It's a solution to the equations of motion. It can be even perturbatively stable when embedded in a top-down construction. And now what I want to do is compute the square of this quantity in gravity. Okay. So when I compute the square of this quantity in gravity, I'm going to have 2 types of solutions. I'm going to have solutions where we take the 2 disconnected genus 2 surfaces and just fill them in some way. And these are called handle bodies. They look something like this, where the green circle is a cartoon for filling in of a cycle. And if you look at the dominant answer for the disconnected handle bodies, you'll get something like this, where beta here is related to a moduli of the genus 2 surface. I'm taking the simplest genus 2 surface, which has a Z3 symmetry in a single moduli. And then you can, you know, study the wormhole. And because the metric is so simple, you can just evaluate the on-shell action, and the on-shell action just vanishes. So you get 1, right? Because we have e to the partition function is e to the on-shell action. Okay. And now the question is, how do we reproduce that from the CFT? Okay. And I should say that, you know, this 1 here, this is really the lack of factorization, because if I had put a beta and a beta prime here, here's really where the function, the non-trivial function of beta and beta prime would be. Okay. So this 1 is an avatar for the lack of factorization. So the question is now, how do we do that from the CFT? And obviously, if we could do a microscopic calculation in the CFT, we would not get the wormhole, because, you know, the microscopic CFT factorizes. But that's not what we're going to do. What we're going to do is, take the square of the genus 2 partition function and compute it with the OPE randomness hypothesis. Okay, that's not a microscopic CFT calculation. That's only using the statistical contribution. And so the square of the genus 2 partition function has 4 OPE coefficients, okay, and some Boltzmann weight. And like I told you, to leading order, they're described by a Gaussian. So let's just do the Gaussian weight contractions. So there's 2 contractions that you can do. The first one leads to this answer here, which you might recognize as being exactly the handle body action, which is not surprising because this is sort of like the trivial square of the partition function. But there's also another width contraction, which you might call a cross width contraction, okay? And if you estimate how big it is and use all the asymptotic formulas, you get the following formula. It's a sum over delta, and it has no large saddle, okay? Which means that for all practical purposes, we could call it 1, okay? It's not exactly 1, and the fact that it's not 1 is related to one loop determinants around a given geometry and gravity, but at the level of the large saddle, it doesn't have any. So we might as well just call this 1.
I have a question.
Yes?
Like, couldn't that term be related to the higher genus contributions to the wormholes?
Absolutely, and that's my next line. Yeah, that's my next line. So, okay, before I answer your question, let me just say that this is very nice because it looks like the Gaussian part looks exactly like what we expected from the previous slide, right? It looks exactly like gravity. But indeed, once we have 4 OPE coefficients, we have to also include the quartic moments. And we computed these quartic moments at genus 3, right? And so if you add in the quartic moments, you'll find that, again, you find something that doesn't have a large saddle, okay? Which means that if you really wanted to go and match now the one loop determinants, what you would need to do is, compute the one loop determinants of the handle body, compute the one loop determinants at genus 3, sum them up in the right way, and check if it matches with what you predict here. I mean, summing up these 2 things, if you want to check if it matches with the one loop determinant of the wormhole geometry, sorry. Okay. So this we haven't done, but at least at the level of order of magnitudes of on-shell actions, it seems to work really well. There's one more interesting thing that happens. So you can look at the genus 2 partition function in a different channel, or instead of having Cijk squared, you have Ciij times Cjkk. Okay, it's called the dumbbell channel. You can square it, and again, this should be described by the same wormhole that we have here. It's just a different decomposition of the surface. And in this case, if you look at the quartic moment coming from the comp channel applied to this dumbbell calculation, you find that this time you have a non-trivial vanishing on-shell action. Okay, delta chi here is the conformal dimension of the lightest primary operator in the theory. Okay, if delta chi is small enough, for example, if you were on supergravity on ADS3 cross S3 or something like that, you would have a very small delta chi, and you would have a new large connected saddle that is bigger than the genus 2 wormhole. Okay, that's what the analysis predicts. And it's kind of interesting if you ask, how big does delta chi need to be for this saddle to exist? And you work it out and how it depends on C. It happens, the bound happens to be exactly that it needs to be smaller than the weight of a Z6 conical defect in ADS3 gravity. Why that is, I don't know. I'm sure it has some explanation. At this stage, it's kind of like numerology. But we found that to be quite interesting. But this is a very heavy lightest primary operator, right? So if you have supergravity with an internal space next to it, you will have operators that are much lighter than this and that are order 1 in the central charge. Okay, so that seems to be interesting. And let me just end with some open questions. So the OPE randomness hypothesis seems to predict this new wormhole solution that we just found. Why have we not found it in gravity? The fact that it depends on the scaling dimension of the lightest operator might make you think that maybe it's matter supported. So maybe that's why we haven't found it yet. But it would be very interesting to look for it. And more generally, there seems to be 2 possibilities, and I still more or less every day oscillate between the 2. Is that whether if you use all the asymptotic formulas that you can derive from crossing invariance and modular invariance, plus you use these Haar averages and typicality. Okay, does that completely predict what the wormholes should be? Or on the other hand, are the wormholes in gravity encoding everything that you could not predict just from asymptotic formulas and typicality? Are the wormholes exactly everything else, all the other parts of the statistical distribution that you could have never extracted from just doing like a one-sided CFT calculation? And so I don't know, this seems to be the big question mark for me, and it would be really nice to figure that out. But okay, I'm wildly over time, I apologize. Thank you for all the great questions and for your attention.
Let's thank Alex for a very nice talk. Are there questions?
Yeah, I just have a question about the counting. Hey, Alex. I just have a question about the counting you and Shiraz were doing about the genus G surface.
Yeah.
At least for the genus one, it seems to be that the Z1 is e to the S. It's not order one, right? It's not clear to me that the genus dependence of ZG is just orders. The torus is e to the S size. So genus 2 for a general generic modulus, I don't know if it's order 1 overall.
Yeah, I guess the problem is that what's a bit tricky is the C. So, right? So Z at G equals to 1 is e to the C over 12 4 pi squared over beta.
But yeah, you can write that as roughly e to the S, right?
Yeah, e to the S, or maybe e to the 2S or S over 2 or something like that, right? There's also a difference is that this is canonical, right? So you have to you have to transfer it back to microcanonical and estimate things, and so there's various factors that enter in doing that.
Yeah, but I think the exponent there will be 1 in the exponent multiplying the S. There might be prefactors, but
yeah, e to the, so you're saying it's e to the S.
Yeah, so for higher genus, it might be enhanced, with
it is. I think for G equals to 2. Remember, I was writing e to the C over 4, I think, pi squared over beta or something like that. That's the handle body solution. Okay. So this is also, you could also rewrite this as some power of the some number
so
times
you would need this overall scaling together with the counting that Shiraz was doing to figure out the size of C squared.
Yes, and the saddle transform between canonical and microcanonical. But I think the conclusion that sort of Shiraz quick thumb rule, what it highlighted is that you also need the conformal blocks. You will not get the counting correctly if you don't take into account the conformal blocks.
Okay.
So, sorry, are your conjectures not correct for a generic conformal field theory of central charge 20 and at temperature of order 1?
So that you cannot do. So okay. So statements like ETH are always meant to hold in the thermodynamic limit.
But so go to very high energies in your conformal field theory, even though it doesn't have very large central charge.
That's fine. That's perfectly fine. We conjecture that it would hold there.
Okay. So suppose we take C as order 1, temperature order 1, and we still want the.
But sorry, that's not very high energies, right? That'll be order 1 energies.
By temperature, I just mean modulus of your torus.
Yeah, but I think if you want to probe the high energy states of the theory, you need to go to very high temperature.
I see. What I was trying to do is to see the contribution of very high energy states, even though the moduli were fixed. And you say those would just be suppressed. So it's only
those are going to be killed by the Boltzmann factor, I think. So those we will not see.
Thanks, Raghu.
Yeah.
I have one small question. I mean, I guess it's a bit of a confusion. So in this talk, you mentioned, you talked about the this ORH, which is a statement about conjecture about the behavior of properties of the statistical distribution of this OPE coefficients for a chaotic theory, and then there were some other movements of these OPE coefficients that you computed from crossing symmetry, and those things agreed with the simple non-chaotic systems, right? So one should kind of make two classes, right? One is kind of the things that you believe to be true only for chaotic theories, and then there are some moments which are just obviously valid in some sense, which you can even compute from some integrable simple theories, right?
Yeah.
Now, can we see that it's only the former class that is responsible for the wormholes business and not the latter?
No, I think both enter. So Yeah. Okay. So there's two sides to your question, right? The first part of what you said, I completely agree with. And I think if we want to go back to ETH, you know, in ETH, if you look at the matrix elements that look like this, RLM, and you could continue for as much as you want with this sort of special cyclic contraction, that's what enters in a 4-point function. And, you know, the 4-point function is probably going to be order 1 in a free theory and in a chaotic theory, right? So the average value of this particular thing is going to be the same in both theories. So this is sort of the equivalent to what I was playing here. There's other types of things that you cannot obviously get from, you know, from a one-sided calculation, a correlation function, which is like just the 4th moment of an individual matrix element, right? So this will not be constrained by any known correlation function. So maybe this is the type of thing that's going to be very different in a free theory and in a chaotic theory. The problem is then we're back to sort of solving directly, because I don't know how to compute or constrain this at all from first principles. But you're right, is that something like this will probably be able to tell, even a coarse-grained version of something like this is going to look very different in a free theory and in a chaotic theory.
I see. But ORH is not about, sorry, maybe, so what exactly is the ORH?
Yeah, ORH is meant to hold for chaotic conformal field theories, not for free theory.
Right? Yeah, and that is a statement about what? Squares of Cij square.
Well, no, that's the statement really about individual OPE coefficients. Right? But of course, if it's true, then it constrains
squares of.
No, even individual, Cijk, for example, or CAVI. Right? And it says that these should be approximately random.
I see. But if you do square, then it kind of is generic again, right? I mean, it's again kind of the.
If you square it an average, then all of a sudden you're in a regime where it's fixed or constrained by modular invariance.
Yeah, right.
But that doesn't, of course, fix the individual ones, and that's the point. So you know, really, the strength of ORH, just like the strength of ETH, is in, you know, the statistical distribution of the individual things, not the average of a square. The average of a square can look, you know, similar in not in integrable theories.
I see. Now, so this wormhole discussion that you had towards the end, there can one deduce? I mean, can one make sure that if you use properties only of these averages which follow from, you know, crossing symmetry, you cannot quite conclude anything about the. I don't know how to make sure, how to ensure that, but you know, basically you want the wormholes only to be property of this chaotic systems, right?
Yeah.
So I don't know. I mean, this is not a very well posed question, but somehow can you say that you know, this integrable theories, they will not produce any wormholes basically?
Well, okay, so that's a different question, and there what you could do is you could study the theory at the integrable point. For example, in holography, you could go to the symmetric orbifold point in 2D and try to study square of partition functions and things like that. Like Eberhardt has done some work on this, and there you don't expect to see wormholes. But you've also pushed the theory in its integrable regime, or at least free regime, and so yeah, somehow the way I like to think about wormholes is that they're telling you about certain chaotic dynamics in a particularly simple way. Gravity manifests, you know, the true chaotic nature of the dual CFT in a particular simple way, but that is only expected to hold in the chaotic regime.
Okay.
Now, how this relates to OPE coefficients, I think that there's a calculation that needs to be done, more refined, including one loop determinants, is that, you know, you really take all the quartic moments that you know, you compute all quartic moments from the all genus 3 partition, all decompositions of the genus 3 partition function, plus the Gaussian part. You plug in to the OPE randomness hypothesis for the square of the genus 2 partition function, you compute, and then you check against the one loop determinant from the wormhole. Does it agree or does it not agree? And that's what needs to be done that we haven't done. It's sort of pretty complicated calculation. but that will sort of tell you whether or not gravity encodes new information that you would, because you see, if the two things don't agree, it's still not a problem for the ORH. It just tells you that you have to introduce by hand a quartic moment for Cijk to the 4, right? You introduce that by hand such that you fix the answer. It's not a problem with ORH, but it just tells you that there's a new part of the statistical distribution that you really could never have predicted without having calculated the wormhole itself in gravity.
Sorry, I didn't understand that. What is this new statistics that you can get from two sides that you could not have got from one side?
Something like this, Cijk to the 4th, right? So if you really write Cijk to the 4th, there's no, you see, because in a CFT, any partition function or correlation function, a heavy state is only ever repeated twice in an OPE coefficient, right? This is, now we're talking about the 4th moment where all of them have been identified to be the same. I have no way how to calculate or constrain an object like this from first principles on one side in the CFT. And, you know, in the statistical distribution over the OPE coefficients, you know, there's a bunch of things, you know, it's e to the whatever, there's some generating function, and here there's a coefficient, and it's allowed to be non-zero from first principles. Nothing prevents it. What I don't know is whether really it is 0 or not in gravity. Somehow one needs to go compute and check. And but if it's non-zero, I think it also tells you that there's some part of the statistical distribution of the microscopics that you can never guess from first principles. Like you really have to, gravity is, you know, gravity is the very smart tool that gives you access to this number, but you would have never guessed it directly from the CFT, except if you had like when to calculate, I mean, except if you had like solved the theory.
So yeah, this is, I guess this is the distinction that I kind of wanted to get clear in my head. I see. So now it is clear. So if you see that there's something else, then that would be the part of, you know, that you would add as a new hypothesis, right? That's how it should be.
Yeah.
For chaotic theories. Yeah.
I don't know which one is better. You know, in some sense, well, okay, if this thing does exist in the CFT and gravity has access to it, and there was no way to get it from first principles in the CFT, then, you know, we're going to be astonished once again of how smart gravity is, right? If that term is 0 and you can predict everything from one side plus typicality, or Haar average, then it's also remarkable because somehow gravity is the theory of typicality. So I don't know. So both possibilities are exciting, and I oscillate a lot. But there's a calculation that needs to be done to sort it out.
But in the second case, there would be no check of this idea, right? I mean, sorry, in the first case, I suppose, where
in the first case, there's no check. You just have to say, yeah, exactly. In the first case, there's no check. You get something new from gravity that you cannot explain any other way than doing this.
Well, there is a check in the sense of your prediction, right? You had some predicted new saddle, and isn't that?
Oh yeah, the new saddle is something yet different.
Okay.
We could even just stick to the other channel, the genus 2 partition function, where there is no new saddle.
Yeah, actually, I wanted to ask you that went over a bit quickly. If you could quickly review what the new wormhole or the thing that is missing was.
Good. So the idea is that we're going to look at the dumbbell channel. It's slightly different, right? Okay, it's a different decomposition of the OPE coefficients, and we're going to compute the square of that. Okay. And in the square of that, so now
just to understand, the dumbbell channel is you make the tube in the middle of the genus 2 surface long. Yeah.
Yeah. Yeah. It's, well, you make all three. We're always making all three of them long in a symmetric way, but it's making these 3 cycles long together.
Yeah.
Instead of what it was before, which was these 3 cycles. Okay.
Okay.
And now you compute the square of that, and you use the quartic moment that you get from the COM channel. The COM channel is at genus 3 is this. Okay. That also involves 4 OPE coefficients. It's a particular quartic moment, and you feed it into the calculation of the square of this. Okay. And when you do that, you plug all the formulas that you have extracted, and you get this. Okay, and that's now a large, exponentially large saddle, right? It has an e to the c piece. So it's a big classical saddle.
And just at the level of the logic between the comb and the dumbbell, how did the delta chi get in?
Oh, that's because it comes in. Yeah, very good. It's because the quartic moment. So the function that enters in the quartic moment coming from the comb depends on the lightest operator in the theory.
Okay.
That's it's not. So the point is that when you do these cross-channel things, sometimes you cannot keep the identity because the identity gives you 0. So you have to go to the first excited state.
I see. Okay.
The same thing happens for torus one-point functions.
Okay, I got it. Okay, thanks.
So then that's what seems to happen, and you plug it in and you get this.
Mm-hmm.
So this looks like a geometry that's connected, right? Because again, had I picked 2 different moduli, there would be a beta and beta prime. It looks like some connected geometry that has a large on-shell action, and that's bigger than the genus 2 wormhole. But we don't know what this corresponds to in gravity.
So, but this is a prediction of ORH and typicality, right?
Yes, in principle, but again, you could always, that's where it gets a bit complicated, is that you could always add in by hand a 4th moment to kind of get rid of, of this.
But you were saying, you were presenting a scenario where, just this.
Oh, yeah, very good. Yeah, so if you can show that this solution cannot exist in gravity for some reason, then I think, yes, you have ruled out typicality and exactly.
So that would be, so this would be a test, right, of this hypothesis.
Yeah, this is a test in some sense. Yeah.
Okay.
It's a different test than the one before. Maybe it's an easier one because you don't even need to compute one loop determinants. You just have to look for a solution.
Sorry, one before meaning which one?
Sorry, say that again.
It's a different one than one before.
Oh, then the one where you go to the other channel where you do the square of this, and you match one loop determinants using all quartic moments that you know.
Yeah.
That will also tell you.
Yeah.
So in general, there are for a generic quantum gravity theory, there would be higher loop corrections apart from the one loop correction, right?
Yeah. So in principle, you have to match them all.
Yeah,
that's right.
So what would that correspond to on the CFT side?
Oh, I think one way to say it is that you should really be matching conformal blocks. So conformal blocks will encode this loop information. If you're in pure gravity, let's for now say that we're in pure gravity, then the only loops that you have are loops of boundary gravitons, and they're non-trivial, but they're all captured by conformal blocks. So that would be taking into account the arbitrary 1/c expansion of the conformal blocks.
Okay.
If somebody sends something in the chat, I imagine somebody's leaving or something. Can't read it, but
so
Raghu sent a message saying.
Raghu said he's out. Yeah, okay.
So if there are no further questions, thanks Alex again.
Thank you very much, Alex. It was a wonderful talk. And thanks
a lot.
being
it was a lot of fun.
patient
Thanks for all the great questions. It was a very fun talk to give. Thanks to all your interesting questions.
Great.
Great.
Bye.
And have a good evening, I guess, for you guys.
Yeah.
Bye-bye.
Bye.